Hello everyone, I am Monika from BSc Chemistry Honours Final Year. Today I am going to read a chapter Electronic Spectroscopy for Audiovisual Impaired Student. So now let us start reading of chapter Electronic Spectroscopy. In this branch of spectroscopy, information about the molecule under investigation are obtained from the various types electronic transition taking place. Depending on the types of electrons present, bonding sigma pi electrons and non-bonding n electrons, different types of electronic transition occurs. The term electronic spectroscopy is used for the study of transition between different electronic states, which lie in visible and ultraviolet region of EM spectrum. Electronic transitions are accompanied by vibrational and rotational energy changes. The rotational changes produce rotational fine structure, while the vibration energy changes produce vibrational coarse structure in electronic spectra. Again, in case of the molecules containing more than one types of electron, several transitions may occur resulting in the formation of several bands. Electronic transition: when a molecule absorbs ultraviolet and visible light, its electron get promoted from ground state to higher excited state. During excitation, an electrons get excited from a bonding to antibonding orbitals. Possible electronic transitions of bonding sigma pi electrons and non-bonding n electrons to antibonding sigma star and pi star orbitals are: first is sigma to sigma star transition. In this type of transitions, a bonding sigma electron is excited to an antibonding sigma star. As the sigma bonds are very strong, so this process requires very high energy. This type of transitions requires radiations of very short wavelength. For example, saturated hydrocarbons like methane, which has only CH bonds and can only undergo sigma to sigma star transition, show an absorbance maximum at 125 nanometer. Absorption maxima due to sigma to sigma star transition are not seen in typical UV spectra 200 to 700 nanometer. N to sigma star transition. In this type of transition, a non-bonding N electron is excited to an antibonding sigma star orbital. These transitions usually need lesser energy than sigma to sigma star transitions. They can be initiated by light whose wavelength lies in the range 150 to 250 nanometer. For example, saturated compounds containing atoms with non-bonding electrons. Lone pairs are capable of showing N2 sigma star transitions. Organic compounds undergoing this type of transitions are halides, alcohols, ethers, aldehyde, ketones, amines, etc. The absorption maximum of such transitions depend on the electronegativity of the atom containing the lone pair of electrons. If we absorb the absorption maxima of CH3Cl, CH3I, it can be seen that the absorption maxima of CH3Cl is around 174 nanometer, while the absorption maxima of CH3I is around 260 nanometer. This is because chlorine being more electronegative than iodine, it takes higher energy, lower wavelength for exciting the non-bonding electrons. The molar extinction coefficient for the molecule is found to be higher, in which the N2 sigma star transition takes place radially. Thus, out of CH3Cl and CH3I, CH3I will have higher molar extinction coefficients. Similarly, amines absorb at higher wavelength in comparison to alcohols. as oxygen is more electronegative than nitrogen. Hence, Emax molar extinction coefficient of amines are higher than the alcohols. Third is pi to pi star transitions. In this type of transitions, pi electrons are excited to antibonding pi star orbitals. These transitions require lesser energy than N2 sigma star transition, and hence radiation of longer wavelength can also initiate such transitions. For example, molecules containing pi electrons, unsaturated centers, double or triple bonds are and also aromatic rings shows pi to pi star transition. Organic compounds undergoing this type of transitions are alkenes, alkynes, aldehyde, ketones, cyanides, azo compounds, etc. The introduction of alkyl groups to unsaturated centers increase the wavelength of absorption by 3 to 5 nanometer per alkyl group. Fourth is N2 pi star transition. In this type of transition, non-bonding electrons are excited to antibonding pi star orbitals. This type of transition requires least amount of energy out of all the electronic transitions. For example, the compounds which involves non-bonding n electrons and pi electrons show both pi to pi star and n to pi star transition. Compounds undergoing this type of transitions are carbonyl compounds, nitriles, C double bond S, N double bond N, etc. The low energy N to pi star transition occur at longer wavelength than pi to pi star transition. Usually shorter wavelength transitions are more intense. The energy order for various transitions can be shown as sigma 2 sigma star greater than n2 sigma star greater than pi 2 pi star greater than n2 pi star. Various types of electronic transition occurring in ultraviolet and visible spectroscopy are shown in figure 3.1. In figure 3.1, we show types of electronic transition between bonding sigma, bonding pi, non-bonding and antibonding pi stars, antibonding sigma star. Selection rule for electronic transitions. There are mainly two selection rules which should be followed for an electronic transition to occur. These are Laporte selection rule and spin selection rule. Laporte selection rule. According to this rule, the only allowed transitions are those which involve a change in parity. G-rad to ungerad, G to U, and ungerad to Grad, U to G are allowed, while Grad to Grad, G to G, and ungerad to ungerad, U to U are forbidden. Spin selection rules. According to this rule, the only allowed transitions are those which involve no change in spin state. Transition from singlet to singlet, triplet to triplet are allowed, while transition from singlet to triplet and triplet to singlet are forbidden. Born-Oppenheimer approximation. This approximation was proposed in 1927 in the early period of quantum mechanics by Max Born and J. Robert Oppenheimer, is still indispensable in quantum chemistry. In this approximation, Born-Oppenheimer approximation, it is assumed that the motion of nucleus and electrons in a molecule can be separated mathematically. The total wave function psi total can be written as a product of electronic and nuclear components, i.e. psi total is equal to psi electronic into psi nuclear. The complication that arisen while solving for the total wave function was simplified by Born and Oppenheimer in their approximation. In Born-Oppenheimer approximation, two simple steps were used to solve for the psi total. In first step, nuclei are fixed at a certain configuration, usually equilibrium configuration, and then the electronic Schrodinger equation is solved to get wave function psi electronic, which depends only on electrons. In the second step, the nuclear equation is solved to get the wave function psi nuclear, which depends only on nuclei. Application of Born-Oppenheimer approximation can be discussed taking benzene as an example. Benzene contains 12 nuclei and 42 electrons. It has a total of 162 variables. 12 into 3 is equal to 36 for the nuclei, 42 into 3 126 for the electrons. In order to obtain the energy and wave function of this molecule, it is necessary to solve the time independent Schrodinger equation. For benzene, this equation is a partial differential eigenvalue equation in 162 variables that contains the spatial coordinates of electron and the nuclei. During solution in the first step, the nuclei are fixed in equilibrium configuration, and then the electronic wave function is solved psi electronic. As the nuclei are fixed, so the wave function depends only on 126 electronic coordinates. In the second step, only the nuclei is considered, so the wave function depends on 36 nuclear coordinates. In this way, the solution was made simpler in Born-Oppenheimer approximation. This approximation is an important tool for quantum chemistry as well as molecular spectroscopy. Under this approximation, it is quite easier to get the wave function for large molecules. On the other hand, if this approximation is not considered, then only the wave functions of lightest molecule S2 can be solved. The success of Born-Oppenheimer approximation is due to large difference between the masses of the nuclei and the electrons. Vibrational core structure. The electronic, vibrational, rotational energy of a molecule are completely independent of each other, and hence the total energy of molecule may be given as E total is equal to E electronic plus E vibrational plus E rotation J. In terms of wave number, the above equation may be written as E total is equal to E electronic plus E vibration plus E rotational centimeter inverse. Thus, a change in total energy of the molecule may be written as delta E total is equal to delta E electronic plus delta E vibration plus delta E rotation per centimeter. The approximate magnitude of changes generated by the electronic, vibrational, and rotational energy are delta E electronic is similar to delta E vibration into 10 to the power 3, similar to delta E rotational into 10 to the power 6. From the above magnitudes, it can be mentioned here that the vibrational changes will produce a coarse structure, while the rotational changes will produce a fine structure in the spectra of electronic transition. Thus, in order to understand the coarse structure in the spectra of electronic transition, it is important to ignore the rotational changes. Hence, without taking the rotational changes into consideration, equation first may be written as E total is equal to E electronic plus E vibrational centimeter inverse. Again, the pattern of the vibrational energy levels can be given as E vibration is equal to V plus 1 by 2 omega E minus V plus 1 by 2 whole square omega E x centimeter inverse, where V is equal to 0, 1, 2, 3. Omega E is the oscillation frequency expressed in wave numbers, also called vibrational wave number. Xc is the corresponding unharmonicity constant. Combining equation 3.2 and 3.3, we can rewrite E total is equal to E electronic plus V plus 1 by 2 omega E minus V plus 1 by 2 whole square. E x is centimeter inverse. For two arbitrary values of E electronic, E dash, E double dash electronic and E dash electronic, the vibrational cause structure of the band formed during electronic absorption from the ground state V double dash is equal to 0 to highest state V dash are shown in figure. From the figure, it is clear that the spacing between the upper vibration level are smaller than that between the lower. This is because an excited electronic state channel corresponding to a weaker bond in a molecule and hence a smaller vibrational wave number. The spacing between the lines decrease with increase in frequency. This is due to the unharmonicity of the upper state vibration which causes the excited vibration level to converge. Conventionally, the transitions are represented as V dash, V double dash, 001020, etc. under high resolution. The lines formed from the different transitions are seen as separate lines. However, under low resolution, a set of lines appear as diffused and broad, and hence such a set is called a band. Moreover, in a set of lines, as the value of V dash increases by 1 unit, so such a set of lines is also called a V dash progression. The study of a band spectrum enables one to get the values of vibrational wave number and unharmonicity constant for both the ground as well as excited electronic state, and also the separation between the electronic states. This is the recording of for audio visible impaired students. Thank you.